Okay, so this is example number 2 on projectile motion. Basically got the same question again, that we just slight variation. We've changed the initial velocity. It's now at 18 meters per second, and we've changed the angle from which it's launched and the launch height. It's now at 30 degrees above the horizontal plane. It's not very clear, but the height, the initial height, is 6 meters off the ground. So once again, we're going to go through the steps. So again, the first thing to do is to break down your initial velocity vector into its x and y components. Ux is 18 cos theta, and initial velocity in the y direction is going to be 18 sine 30 degrees. Plug in your numbers, and that gives you, for the x direction, you've got initial velocity of 15.588 meters per second, and in the y direction it works out to be a nice even 9 meters per second. So once again, I'm not going to labor these points too much. I've done that in previous videos, so if you're a bit unsure, go back on the previous video. So I've got the initial velocity in the x direction, displacement in the x direction, and the time in the x is equal to time in the y, which we just called t. We know that the acceleration is going to be negative 9.8 meters per second, and of course that brings me to my next point. That is the frame of reference. So I'm going to come back up here. I'm just going to make it very, very obvious. The frame of reference goes like this: positive, negative, positive, negative. Okay? So once again, that gives me a negative acceleration and a negative displacement in the y direction. Exact same as the last time. We're going to solve the velocity in the y direction, final velocity in the y direction. I'll use that same formula. Final velocity in the y direction is equal to the initial velocity in the y direction plus twice the acceleration times the displacement. Plug in your numbers, and you get negative 198.6. Take the square root of that. You must remember, so again, I'll put a little asterisk around this. You must remember that your calculator is going to give you a positive number, but you must remember that because this velocity has to be going down, therefore it is negative. Okay, so just based on your frame of reference. Again, we've done that in the previous one, so I'm not going to overlabor it. Next step is to find the time. Is the time in the x. Time in the y is going to be the same as time in the x. We'll use that for the displacement. So the final velocity in the y direction is equal to the initial velocity in the y direction plus the acceleration times the time. Just putting on the y's. I don't need to put the y on the time because it's irrelevant. Plug in your numbers and you get 2.356 seconds. The last thing to do then is to come back to the velocity in the x direction, which we must remember was a different number. It was 15.588 meters per second. It was this initial velocity right here. You plug in your velocity times the time that we've just calculated, 2.356 seconds, and that works out to be 36.73 meters, or 36.7 meters, to enough significant figures for our simulator. And we'll do that now. So we worked out to be 36.7 meters, 36.7 meters. Launch and hit presto. Boom, there we go, target. Please notice air resistance is switched off, so there's no drag coefficient here. So therefore there is zero acceleration in the x direction. Okay, next job, which is the tricky part for this, is we're going to look at what the graphs look like for this situation. So the thing to do now is to just have a look back at the initial information we were given and see if we can piece it together into a graph. So we were, I'll start with the y direction because that's the hardest bit. So y, the initial velocity in the y direction we knew was going to be 9 meters per second. We went ahead and calculated the final velocity in the y direction, and that worked out to be just over 14 meters per second negative. Okay, and I've also calculated the time to be 2.35 or 36 seconds. So I lay out my axes like this in a kind of a cross. So I need to have a positive side and I need to have a negative side. And my time, I've got 2, so I'm going in 5 squares here equals 1. So I've got 1 to here, 2 to there, and that puts 2.3 round here, 2.356 seconds, in and around there. So I've marked my initial position, which is here. That's 9 meters per second at time equal to 0, and at time equal to 2.356 seconds, I know my speed is just slightly over 14 meters per second negative. My velocity is just slightly over 14 meters per second negative, I should say. Okay, so at this point now, I'm just going to insert the line. It's not going to be a million miles off. And you can see that this part here, this is the upward displacement. Remember, the area between the line graph and the time axis gives us the displacement. So that's the positive displacement. And the negative displacement, do remember the negative displacement goes between the line graph and the time axis, always, okay? So we should be able to kind of deduce what the total displacement is. We can work this out with a calculator in a few minutes, but we know what the total displacement is. Basically, if I was to subtract the difference between those two triangles, this one here, the positive one, and the negative one that's here, then I should get the overall displacement in the y direction, and we know that that is negative 6 meters because it started from there. So the next thing to notice is that the speed or the velocity goes to 0 at around what looks to be time equal to about 0.9 of a second. So just short of 1 second. There maybe 0.9, I'm going to guess 0.91 or so seconds, something like that. We'll calculate it in a second and we'll just see how that works. Okay, so in order to calculate that time, what I did was I set the final velocity equal to 0, because I know that at the top of the parabola, when the ball reaches the top here, it's not going to have a y component at this point. It'll only have an x component of its velocity. So I'm going to set that as my final velocity, say it's equal to 0, and then solve for the time. So I plugged in my numbers, and lo and behold, I got 0.918 seconds. So my estimation of 0.91 seconds wasn't far off. So the next thing I want to check is to see what is this positive displacement S1, we'll call it. How much is that going to be equal to? So I'm basically going to use the displacement being the velocity, the area under the curve, or the area between the line graph and the time axis. So S1 is going to be the velocity, the initial velocity here, 9 meters per second, times the time up until that point, which is 0.918 seconds. Let me change that here, that's 8 seconds. And divided by 2 because it's a triangle, and that works out to be 8.265 meters. So that's S1, that's the total distance up that the cannonball flew. The next thing I'll look at now is what's S2 going to be here? S2. In other words, how far down is it going to go? So apologies for this. I noticed that I made a mistake. So S1 should actually be 4.1 meters, 4.131 meters, because I forgot to divide this one by 2 because it's a triangle. Anyway, to calculate the change in time for when the ball is now falling, it goes from this point in time here, which is 0.918 seconds, all the way up to the total time, which we calculated earlier, which is 2.356 seconds. Subtract the two the two times, and you've got a change in time for the fall of 1.438 seconds. Sub that into your displacement formula. Displacement is going to be the velocity at the bottom times the change in time and divided by 2 again because it's a triangle. Plug in your numbers and you get negative 10.1 meters as a displacement. Now all you have to do is add up your two displacements and it should give you your overall displacement. So S2 negative 10.1 plus S1 4.1, and it gives us negative 6 meters. Okay, so we now have enough information to be able to draw the displacement time graph. So I'm just going to use what I've just used, the exact same axis for the time. I now change the y-axis for displacement graph, and I have to pull up on a mistake that I made earlier. I had earlier called this one X, and it should, sorry, UX, and it should actually be Y. So at time equal to 0, we've got 0 displacement. That goes up to a maximum positive at the time. Time equal to 0.918 seconds. Then it comes back down. I'm trying to draw this as carefully as I can for the second part, because it's going to come back down. I'm going to have acceleration here, so it's a little bit funny. Something like that. So you'll notice that the actual curve of the displacement time graph will look pretty much identical to the trajectory of the actual ball itself, the cannonball itself. So the trajectory would look something like this. This is going to look something like that, and this is going to look very, very similar to that. The last thing then to see for the y direction is the acceleration, and of course that's the simplest graph of all. It's a straight line at negative 9.8 meters per second squared. While I'm on that, just for a moment, let's show you one last thing. We know that the area under the line graph, between the line graph and the time axis for a velocity time graph will give us the displacement. But what are you going to get if you take the area between the line graph and the time axis for an acceleration time graph? But if you just follow the units, you're going to have negative 9.8 meters per second squared times your time, 2.356 seconds. And if I plug them in, then I get negative 23.00, sorry, 0.8888. But what does this work out to? Well, the unit works out to be meters per second, so this must be some sort of velocity. But what velocity is the question? If we have a quick look back, on our velocity time graph for the y direction, then we started at 9 meters per second squared, sorry, 9 meters per second, and we wound up with a velocity of negative 24 meters per second, or slightly, sorry, negative 14, slightly over, it was negative 14.08, I think, meters per second. And if you add up those two numbers, you need to find the difference between those two numbers. So the final is negative 14.08 minus the initial, which is 9. Then you will wind up with exactly what we got there, which is 23 point. So your change in velocity, the total change in velocity works out to be 23.08 meters per second. So your change in velocity in total. So that little piece of information, that little nugget, is disguised under the area, between the acceleration graph, and the time axis.